Dr.
Manoj, your voice is breaking.
Okay, Sugandha, you can start your presentation maybe.
Okay, I thought the problem is
Yeah,
at my
able
end,
to.
so I switched off my
No, I
video.
think problem is at Manoj's end. Manoj,
All
we
right.
couldn't hear you. Yeah.
So I'll just present my slides and then
Yes,
begin,
yes.
right?
Yeah.
Yeah. We have some internet problem here. Please go ahead.
Yeah, I'm just, I don't know why isn't it showing me right now. Give me a second. I just did it. It was working well, but I don't know. So I'll share the whole window, maybe, whole screen, maybe.
Mm-hmm.
So now you can see the presentation, right?
Yes. Yeah.
Okay. Okay. Thank you, Manoj, and thank you, Anupam. So I'm very pleased to be presenting this work, the unit group of an integral group ring. My idea of this talk will be to kind of give an overview or a survey of the work which has been going on about this. So this is not kind of a complete compilation, but I'll kind of try to touch almost all the aspects that I studied over in last 5 to 6 years about the unit group of this integral group ring. All right. So let's begin with the notation. G, I'll always be assuming a finite group by default. In case it is not, then I'll mention it specifically. So ZG is the integral group ring where you have elements which are linear combination of elements of group, and the coefficients come from ring of integers, right? This is a Z module. In fact, it's a Z algebra with the G as basis, okay? So our target is to understand the unit group of this group ring, which we denote by U of ZG. This is the main thing that we have in focus. And along with that, the important subgroup of this center of this unit group is another thing that we are going to lay stress on. So, all right, we have a group G. What are the fundamental problems? Determine U of ZG, determine its center, right? The point is how important, how involving getting the answers to these questions become, right? And what kind of answers we are really looking up to. That is the kind of thing that one looks forward to when you want to understand the unit group of integral group ring and its center. So first part will be laying stress on the unit group itself, and then I'll move on to the center in the second part. Okay, so first description is about the non-trivial units in this group ring. Okay, so what are the trivial units? If you look at elements of group G, they are all invertible. So of course they are elements in this, and we call them as trivial units. So apart from these, what are the units that you have in ZG, right? So I'll give you an example. If you have a cyclic group of order 10, and it's generated by this element A, right? Then this big element that you see on the screen, which has coefficients which are not so nice looking, this is actually invertible. This has inverse, which is right now on your screen, in this group ring. And of course, it is not easy to assess whether a given element is invertible or not, or what are the non-trivial units, and things like that. So of course, the units in this integral group ring are fascinating. One has to, these are not very obvious things. So here are some constructions that we can look up to. A very basic construction: if you have a non-abelian group and you have two non-commuting elements A, B, then you look at this element, which I'm denoting here by eta, and you look at this combination, 1 minus b, A times 1 plus b. And of course, the square of it is 0, because because of the way how it is constructed here. So 1 minus eta square, which is equal to 1. This easily gives us that 1 minus eta and 1 plus eta, these are both units in ZG, right? And similarly, if you have any nilpotent element, if you have eta to the k is 0, 1 minus eta will become a unit in ZG, right? And to those we call it unipotent units. So this is one way of constructing non-trivial units if you have two non-commuting elements. And there are other constructions of non-trivial units. Most prominently, which is used, is of Bass units. And in fact, they quite well cover up the units, the non-trivial units in abelian groups. So cover up in the sense, if you look at the subgroup generated by all Bass units, Bass cyclic units as we call them, then they generate a subgroup of finite index and unit group of ZG. I'll come to that a little later about the subgroups of finite index, how important those are and why do we study and things like that. So Bass units is a very important construction as far as abelian groups are concerned. Then another construction is of bicyclic units. And over the time, it turned out that Bass units and bicyclic units suffice for very good classes of finite groups when you talk about these large subgroups or subgroups of finite index. Then there are alternating units, Huishman units, which were again constructed in order to study the units in integral group ring, mostly for abelian cases. And very recently, there have been the units called Bovdi units. These are also somewhat coming out of combination of Bass units and bicyclic units. So more or less, it's Bass units and bicyclic units which play a very important role as far as non-trivial units are concerned in ZG for finite group. Right. So more constructions are very much welcome here. Like for the groups where Bass units and bicyclic units do not suffice. I mean, if you take up all trivial units, Bass units and bicyclic units and look at the subgroup generated by them, if that is not of finite index in the whole unit group, then we do not really have any constructions of the units which come outside that group, right? So any sort of non-trivial units, their construction will be a very much welcome thing in this area. Okay, so that was one thing. The other thing is to understand the structure of UZG. Can we describe what is this unit group, given a group G? What is the structure of this group ring, right? So there have been answers for some particular cases. For example, if you look at symmetric group of order 3, then this is seen as a subgroup of GL2Z, having some conditions, right? And similar work has also been there for D4, where again the unit group is subgroup of seen as a subgroup of GL2Z. And in case of A4, it is shown to be isomorphic to a subgroup of SL3Z, right? But in all these cases, it is only the structure which has been talked about, that it is isomorphic to a subgroup of this kind, satisfying some conditions, but nothing has been talked about the explicit units which are in these group rings. Okay, so again, the structure of UZG is a very important thing that one can focus upon. For abelian case, it is quite well understood in comparison to the non-abelian ones. But when non-abelian groups are concerned, there we have just some particular cases. I mean, there could be some more, but it's not that we have good classes covered up for this kind of structure, right? And third kind of description is about generators of UZG. As I said, finding non-trivial units is a big task. And then in case you have, can you find all of them? Can you find generators of UZG? So for that, we do have some answers. Let's have a look. For abelian groups, we know that all the torsion units are just the trivial units, right? The torsion part of UZG is G, and the torsion free part is a finitely generated free abelian group. Right. So more or less for abelian case, the problem reduces to understanding what is AG, what is its free rank, right? And what are the generators? So if one is able to find out that, we do have answer to what is the whole of unit group usage. All right. So this is an important result that one relies upon while understanding the case of abelian groups. Okay, and in the same paper where this result is, given, uh, one can really come up to this point that if G is of exponent, if G is abelian group of exponent dividing 4 or 6, then it is going to have no non-trivial units. You're just going to have trivial units in that case. And yeah, so all right, so here are some answers for the explicit generators. Like if you look at the cyclic groups, so exponent 2, 3, 4, or 6, we are going to have trivial as I mentioned earlier. And for C5 and C8, we do have answer for generators, right? They have single generator. These are of rank 1. And similar answers are also existing for C7 and C9. They both have 2 generators each, and their description is known to us. Then for C10 and C12 also, we have answers. So it's mostly work of Elive et al. That you can see. And C16 and C32 is not too old work, right? It's 2009 that we have some answer for these 2 groups. So the thing is, okay, there are some more cases which can be covered up here. So for cyclic group of prime order, right? And this is also for restricted prime P. It's not for all primes P that we have answer, but it's a good class that they have covered up. This is work of Firas, 2009. Where you can write down the description of generators in terms of Bass cyclic units and alternating units. So there is some answer to what are the generators of the unit groups when you are talking of cyclic groups of prime order. And for prime power also, there is a good answer that one finds in paper of Firas and Kitani in 2015. So this description is in terms of Huishman units. Right, but again, we do have some restrictions on the primes that are involved. It's a number theoretic condition that's there, and then you also have some answers for cyclic groups of order 2p, and the abelian group that you see CP and 2 copies of C2. So the point here is that even for cyclic groups of prime power, prime order, we do not have a complete answer. We do not have one recipe to kind of write down the generators of UZG, right? This is a very basic fundamental question which has been worked upon, but then still there is a lot which can be done in this, even for cyclic groups. Then here are some results which you can see for non-abelian groups, for metacyclic groups of order PQ. There has been some description. It's an old paper, so the description is not very explicit, but there is something which has been, which is known about metacyclic groups. For the case of DP, dihedral group of order P, there is characterization of units of order the units in this known to us. And for specific values of P and for specific values of N, some more results are known for dihedral group of order N. Then for non-abelian groups of order P cube, there is some description of units which is using the fiber products. And again, it's not very explicit, but it's old work. So maybe with the tools that we have in hand now, these can be even more refined. And for S3 and S4, we have complete characterization of units. This is work of Allen and Hobie, 1987-88. So these are few groups which people, tried to handle or, look at while trying to understand generators of this. And to this, we also have some contribution. This is recent work with Leo Margolis and Andreas Bachelet. So in this paper, we were trying to understand the quotient U mod U dash, the abelianization, the unit group modulo its commutator. Because that being abelian, we thought we can have better control because there is a lot more known about center than unit group of ZG. And in the process, we learned that the groups that you see on your screen, the first two groups, they do have a free normal complement to the unit group of these groups that has free normal complement. And for that complement, the generators are known. Okay, so with the help of GAP, we tried to understand the action of this group G on that complement, and we could establish all the relations, right? So this is how we could find answer to UZG for the first two one, and for the third one also, D16 plus that you see here. So the first group is dicyclic group of order 12, and the next two that you see, these are groups of order 16. And we were kind of trying to get hold of all groups of order at least up to 20, right? That's what we were doing. So for the last one, also it was known that it has a torsion-free normal complement, and with the kind of results that we had about that complement, and with some gap calculations, we could write down all the relations. I'm not listing them here because that's a long list that we have. So the unit group of these groups are also identified, right? And the fourth kind of description. So first one was non-trivial units existence that we saw. The second one was if you can give the complete structure. The third one was not just structure. Can you also write down all the units, the generators? And the next one that I'm saying is, even if you cannot write down the whole unit group, can you find out a large subgroup in this unit group? By large subgroup, I mean a subgroup which is a finite index in the whole unit group. Okay, a lot of work has been done in this direction. I also mentioned this in the beginning that Bass cyclic units, they do generate a subgroup of finite index. So it was initially done for cyclic groups, and then it was extended by Bass and Milner to abelian groups, right? There is an alternate recent proof to this result that Bass cyclic units generate a subgroup of finite index and use ZG when G is abelian. There's an alternate proof also. This is a general result by E. Clenart that subgroup generated by unit groups of cyclic subgroups rings has finite index and UZG, but then this was with some restrictions on G, and more or less with the basis of this, there are, if you understand the cyclic groups well, how to get into finite group. This has been this method has been used quite in many papers to get hold of the whole unit group. So we do have answer for dihedral group of order 2n for odd nilpotent groups, where Bass cyclic units and bicyclic units, they generate a subgroup of finite index. And in fact, this has been for some years, this has been trend of understanding for what all groups these two kind of units suffice, in the sense they do generate a subgroup which is large in UZG. There has been an answer to monomial and symmetric groups, right? And people have studied metacyclic groups also, and there we do have positive answer in this direction. Here is a list of all other groups which have been handled. In fact, this is not true for the case of quaternion group of order 8, right? So K8 cross CP that you see here. So here the discussion has been about free subgroups in UZG. So as I mentioned earlier, the subgroups were, the groups for which Bass units and bicyclic units do not suffice, there we kind of need more non-trivial units, some recipes, some units which can cover up the remaining part. So, and there are a lot many papers in this direction where people have studied large subgroups and unit group of ZG. So I'd like to proceed to the center of this unit group now. Okay, central units of ZG. All right, so the first description here is again in terms of what is the group theoretic structure. So because all central torsion units belong to the center of G. So if you remember, I mentioned about abelian groups also earlier, that we have, all the torsion units, they do belong, they are group elements, right? So this is true for the central units as well. So we have that the torsion units belong to the center of group, and the remaining part, this torsion free part, this is a free abelian group, and this is the rank of it and the generators of this. These are the most important things that one likes to study when you want to understand the center of the unit group, right? So this is finitely generated is known to us, and the torsion elements are central elements of the group. This is known to us. So the problem reduces down to determining what is the rank of this group, and can you find out the generators of AG? Can you write down a basis, which I'm denoting here by SG, for this torsion-free abelian group, right? Okay. So let's see what are the results that we have, what is the progress that we have, firstly on the rank, and then I'll talk about the basis, and then some other things. All right, so in case of abelian groups, we have a complete answer for the rank. You have an abelian group, then its rank is given by this formula that you see on the screen. It is dependent on the size of the group G, and this N2 denotes the number of elements of order 2, and this small c denotes the number of cyclic groups of G. So this again is in the work of Higman in 1940. In fact, it seems that prominently this is the paper where all these questions came into picture, and all the major works kind of originate from the questions which have been raised about the unit group from that paper. So the rank of free abelian group, the rank in case of abelian group G is known to us very much in the by the elements, by these parameters, the number of elements of order 2 and number of cyclic subgroups of G. Rank is known to us. All right, so this has an extension. So this is work of Ritter and Segal, 2005. If CG denotes number of conjugacy classes in G, and QG denotes number of Q conjugacy classes in G, right? Q conjugacy means the element X is conjugate to some, the generators are conjugate, right? Generators of cyclic group X and Y, they are conjugate. Then you say that they belong to same conjugacy class. And RG is number of real classes in G. Real classes meaning that if some element belongs to a class, conjugacy class, its inverse also belongs to the same class, then we say that conjugacy class is real. So in terms of these CG, QG, and RG, he gave a formula for rank for finite groups, right? So we do have complete answer for any finite group. What is the rank of the free abelian part associated to the unit group? And this work was carried out independently by Ferraz in 2004. So it was almost the same time period when two of these were working on same kind of things. So if you look at the number of simple components in RG, right, real group algebra, and number of simple components in QG, we denote them by RG and QG. So this Q of G, this happens to be same as QG that you saw in the previous slide, okay? That is number of Q conjugacy classes. And RG is same as number of R conjugacy classes, right? By R conjugacy, I mean that X should be conjugate to Y or Y inverse, right? In Q conjugacy, it could be conjugate to any of the generators, but here we want specifically to Y or Y inverse. And QG, as I mentioned earlier, is same as number of Q conjugacy classes. Then for this finite group, the rank is given as difference between these two. the number of simple components in Rg and number of simple components in Qg. So in a way, if one knows the Viterban decomposition of Rg and Qg, or just the number of simple components occurring here, that is also good enough to know the rank of this unit group, right? Okay, and so the answers for particular cases for alternating groups of order n, we know when for what all values of n this rank is 0. In fact, this rank 0 is very important thing, and I'll talk about that also in next few slides. So rank of the unit group of alternating groups is 0 for all these values of n, and it is 1 precisely for all these values. This was known due to Feraz and Elif et al. This is work of 2004 and 2008, right? So let's see, what more do we know? We know the rank for case when G is metacyclic group as well. So if you have a metacyclic group of order PQ, where P divides Q minus 1, then for this metacyclic group, we know the rank is going to be given by this formula. And in fact, the only solution to this rank being 0 is 3 or 7. So rank being 0 means what? If you look at previous slides, this simply means that this AG does not exist. You just have that the center of unit group is same as the center of the group G, right? Plus minus the center of the group G. That means you just have all the units to be torsion, right? That's why we say that this rank 0 is somewhat a specific case, somewhat an important case for us. And for metacyclic groups of order PQ, where P divides Q minus 1, this is the only solution that we have by this formula. Okay, so I'm not going into detail of what is a strongly monomial group, but for the timing, those who do not know about this, you can take it to be it's a considerable class of finite groups where, abelian bi-supersolvable groups are included in this class. And there is a whole lot of work which is done around this class of groups, which has given us various good results. So this class of groups is, there are strong Shoda pairs which are involved in understanding the Viterban decomposition, the simple components of the rational group algebra. So these strong Shoda pairs are subgroups of group G, and they have certain nice properties which they satisfy. They are good enough to determine all the representations of group G, right? So this rank is given in terms of strong Shoda pairs for strongly monomial groups, right? In case you know of a strongly monomial group and you know a complete irredundant set of strong Shoda pairs of it, then you can write down rank of this. In fact, we have used this formula to write down free rank of all groups of order P cube and P4, right? That was in my doctoral thesis. This is a very useful formula. So let me just recall once again what all we have done for the center. So what we know is that to understand the center, we need to know the rank of this free abelian group AG, and the second thing is about the basis. Okay, so we have seen that there are formulas known for the rank, right, in terms of group structure, the parameters of the group, and at times from the strong Shoda pairs of the group. And the next thing is about the basis of this. Next thing is about generators of AG, right, which gives us complete description about the unit group. So let's see what all do we have by now. So alternating group, a lot of work has been done in this direction. As I already mentioned, the groups for which, this has just the trivial units, those. And for n is equal to 5 or 6, the generators are known to us explicitly. For A5, this work was also done by Lee and Parmenter, although this work was done by Elif for more general cases. Then there are also some results which give you, which tell you about the rank of AN when N is less than equal to 600. So it's not a complete thing, but there are ways of doing this, and it covers quite a good, you know, it has a good coverage of the N's less than equal to 600. And then full description of this when rho of an is equal to 1, this is known, this has been listed earlier also, right? So for an, some work has been done where you know the generators explicitly, not just what is the rank, okay? The method of Young tableau also comes into picture. In fact, that has a very prominent role to play when we talk about alternating groups. Okay. Then for metacyclic groups, it's not the whole class which has been taken up. The only two examples which I could find out were in the recent book of Jespers and Del Rio that you see on your screen. So they have calculated for these two metacyclic groups using some algorithm which was given in Borovich and Shifarovich's number theory book. And this is not very efficient method in general. This cannot be generalized to all metacyclic groups. But yes, it gives us a way how to write down the basis for this free abelian part of unit group of ZG, right? And the same can be also used to write down the answer for D16 and Q16. So these are very particular answers that we have when we are talking about the basis groups. For abelian groups, it's the same as the unit group, so I've not repeated it. We already know in what cases we have the generators. Then you saw we have results for alternating groups. And then for metacyclic groups, we have just for some particular cases that explicit generators are known to us. And then the next description comes again in the form of subgroup of finite index. So in unit group also, we wanted to see if we can have answer for the whole unit group. If not, can we find out a subgroup of finite index? And similar answers have also been tried while studying central units of integral group ring. Okay, so sorry. Okay, so the work has been taken up in this direction, and the last one that you see on the screen, the third one, in this article for strongly monomial groups, generalized Bass units were defined. So these generalized Bass units, they do use Bass units as well as the concept of strong Schoda pairs, which is meant for strongly monomial groups. And with that, they define generalized Bass units. And if G is strongly monomial group, in that case, these generalized Bass units generate a subgroup of finite index in the center of the unit group of ZG, right? And not only the large subgroup, the matter here is also about the virtual basis. Like if you have that large subgroup, can you find out basis for that? So that we are calling as virtual basis, right? So this is the kind of direction which is going on to understand subgroup of finite index in the center of the unit group. And that I'll add off some more directions which are related to this work. So I'll just quickly recall the two things that we focused upon was unit group and the center of the unit group. Unit group, we wanted to understand the non-trivial units or the complete structure or the subgroup of finite index, right? And for the case of center of this unit group, again, similar kind of things. And it was important and good to understand the rank as well as the generators of the free abelian part of the center, right? Sorry. And then we wanted to understand if we can find out a subgroup of finite index, right? Then we took up another direction in this, that how about the index of this large subgroup, right? We've always been talking about a subgroup of finite index, subgroup of finite index, right? So this last article that you see, I mentioned about strongly monomial groups. So we took up this class of a subclass of strongly monomial groups. This subclass was taken up in the same article, and we tried to understand what is the index of that subgroup in the whole center, right? So to understand that index, we just could find a bound. We couldn't find the explicit index, but that bound was also somewhat important to understand how far is the subgroup from the whole subgroup, right? The large subgroup, how large it is basically. So these kind of works are important if you can really find out the index or even bounds on them. Then the two things, lower central series of this unit group and the study of upper central series. It's not as easy as it has been listed here. You saw that even to understand the center, there is a lot of work which has been going on, and there is still a lot which needs to be done. So the problems associated to lower central series, these I have listed 5 problems in this article, which will come up in this sorry, Indian Journal of Pure and Applied Mathematics. So there, the very basic problems on lower central series of the unit group are not known, and there is a lot which can be done in this direction, and that came out analogous to the study of upper central series. And I'll talk about this upper central series a bit. So this was analogous to the known things about upper central series. What do we know about lower central series? And even for finite case, and there is lot. There is very less work which has been done in this direction to understand lower central series of this unit group. While coming to upper central series of VZG, the nice thing is that if G is a finite group, we know that it terminates at 2 steps. It stabilizes at 2 steps. I mean, the second center is same as the third center for all the groups. And wherever you have central height 2, I mean, wherever first center is not same as the second center, in that case, the second center in terms of the first center, right? Z2 in terms of Z1. So that is nice thing about upper central series. And so you have either central height 0 or central height 1 or 2, right? In order to understand, central height 2 is also classified, right? So in order to understand this upper central series, all that you need to know is what are the groups for which the central height is 0. 2 is known to you. In case you understand what are the cases where central height is 0, the problem, you classify that what is the central height of given that group, right? And that boils down to understanding if the central units in VZG, if they are trivial or not, right? If your rank of that free equivalent part is 0 or not. So as I mentioned, that rank 0 is somewhat very important, very considerate things. We are calling these groups as cut groups. This term was coined in our joint work. This was with Professor Pasi and Professor Bakshi. So we tried to understand all the groups G, the finite groups G to begin with, where central units of ZG are trivial. This is how the name cut comes into picture, CUT, right? So in order to understand, so this is one new direction that came, that people have been studying non-trivial units for a while. How about the groups where these do not exist? How about the groups where these are just the trivial ones, right? So we worked for the finite case. We could find out some very basic but very interesting properties. So classification of groups for which rank is 0, free rank is 0, or saying that there are only the trivial units in the center of unit group. The classification of such groups, that is one good direction to work with. Then what are the properties of these finite cut groups? In fact, they have very restricted prime spectrum. For nilpotent groups, it's just 2 or 3. Right? All nilpotent groups, the prime spectrum turns out to be 2 and 3. For solvable groups, the prime spectrum turns out to be 2, 3, 5, and 7. There are no primes greater than 7, which divides the order of a solvable cut group. So such interesting properties could be observed. What other things? This is quotient closed property, and so on. There are various properties that one can find out for these groups. And of lately, we have also studied, we are studying, this is an ongoing project, what are the prime graphs, because it has a very restricted prime spectrum. So can you list down what are the possible prime graphs which are associated to cut groups? And there is a whole lot of work which has been going on in cut groups. It's only 3 or 4 years that this work has been going on, but there is a sequence of papers which have come up. And not only that, we look at from this integral grouping point of view. It has, this can be seen as generalization to rational groups. And we call it inverse, semi-inverse, inverse semi-rational groups in that case. And there are a lot of equivalences that one sees. It also has impact in the on the Vidarbhan decomposition of QG. The division rings which come into picture in the Vidarbhan decomposition, they have very restricted structure. So all these kind of properties around cut groups, they are very important. And more importantly is that classification of cut groups gives you the answer to the upper central series of VZG. So yeah, I'd like to stop there. Thank you for your patience.
All right, let us thank Sugandha for this very nice talk. And this is time for interaction. So please ask questions or make comments or suggestions.
Yeah, maybe I can make a comment, Manojji.
Yeah, please.
Yeah. So regarding the center of the unit group of ZG, a subgroup of finite index, there is a work beyond what Sugandha you have mentioned. That is on generalized strongly monomial groups and subnormally, more particularly subnormally monomial groups. That was covered in Gurleen's thesis. Maybe if you look at that, then there are more classes covered there where she can find a subgroup of finite index in the central units of ZG for a much larger class of groups, subnormally monomial groups.
Yes, I'm aware. I missed mentioning that here. I'll take a note of that. Yeah.
So I have a stupid question. So suppose you know something about the center of the units, like the rank of this torsion-free business. Can you say something from this the center to the whole units?
Well, yes. In fact, as per my understanding, the problem which came down to center was in order to understand the whole unit group, right? So I cannot give you explicit answer right now. I mean, but yes, there has to be. These two things are not like, I mean, they do coincide for abelian case, and how much they differ in other cases, there is some connection for sure.
Okay.
Can you repeat your question, Manojji? I couldn't get your question.
So the question was, in case you understand the center, what answer does it give to the whole unit group?
Okay. Not very well studied. Yeah.
Are there more questions?
Can I ask something?
Yeah, please.
Yes.
Yeah. How much? I mean, in general, knowing something about the unit groups generated by subgroups, does it play any role as far as the unit group? So, like you're looking at ZG, if I know something about ZH or some special subgroups H, does it at all influence anything about the structure?
Yes, yes. So if you remember, I mentioned about bicyclic units. So this that was used for abelian groups. So it was in the so that was in this direction. What you are saying, that if you have units of ZC, how do you go to ZG if G is abelian, right?
Right.
Breaking it down to the yes, of course, that has connection. So that was the work of Clenard that I mentioned. That if you have understanding of the cyclic subgroups, you can give some information about the unit group.
But does it work for non-abelian? No. Non-abelian groups?
That was for all finite groups with some
All
restrictions.
finite groups. Okay.
With some restrictions. I mean, it's not for just for abelian groups, but it is not for all finite groups as well.
Okay. Thank you.
Geeta, in fact, that was the aim while defining Shoda pairs kind of things, to understand it from the subgroups. And when
Right.
you write
Induce
units
it up.
from the strong Shoda pairs or Shoda pairs, that is the entire motive behind that.
Yeah, yeah, yeah. So it's a kind of induction which is happening up here.
Right, right.
There is a question on chat by somebody.
Let me see.
Sugandha, maybe you can stop presenting. Then we
Yeah,
have
okay. Okay, so the question is, if we replace the ring of integers by a finite field, then units of FG are known or not. Well, I've not worked in that direction because comparatively, when you go to fields, the things become easier. The challenge was here to understand ZG. So my whole focus has been on integral group ring, because I was initially working with the structure of QG. And QG is a rational group algebra. I was trying to understand this rational group algebra, and then I wanted to see its impact on this integral group ring, right? So if you replace Q by some other field, then it has impact on ring of integers of that, for sure. So if you replace it by fields, the answers are going to be, I mean, you have more liberty with the coefficients to work with, right? But right now, I mean, I've not worked in that direction.
Yeah, that is in fact well understood. I mean, if you take a semi-simple case and a finite field, there the Vetaban decomposition is well
Certainly,
understood.
Yeah.
And therefore
certainly there is no division algebra that will be helpful.
Yeah.
Right.
So actually, I have another question in the direction of Geeta asked. So if you know something about the quotients of the units of the quotients of the group, certain quotients, then can that be some knowledge that knowledge can be taken to the full?
Maybe. Yeah, some kind of lifting you are saying, right?
Right.
Right. I cannot say that. I mean, how to go about that construction. But that's something which needs to be taken care of. Subgroups we have been talking about, but why not quotients? Yeah. I'll have a look at if there
But
is
Sugandha,
something.
when you bring Shoda pairs into the picture, the subquotients H mod K will come into the picture, and that will play a role.
Definitely. But then in general, if you know about G mod N, how to go upon to G, that's, I mean, the construction.
Okay.
That's what
That is
he
good.
asked for, right? Yeah, I mean, from units
Quotient.
of G mod N to the units of integral group ring of ZG, right? That was the question.
Yes,
That
yes.
is.
Are there more questions?
I don't know whether is it right. Still, I'll try to ask one question. So, if we have a module over like kg, for k is a field, that's there is a representation theoretical equivalence. So, if we have a
Mm-hmm.
module over zg, then
Mm-hmm.
are there something which we can conclude about something in about like units of zg or some of these questions? Like if we go for module over this ring, and can we do something?
Uh, we will need more tools, I guess. I mean, because we are uh, trying to generalize, but what I am aware of is that if you go from, I mean, if you want to look at ring of integers of some number field, then there are results in this direction. But in general, if you have a module, then if you can generalize or not, I don't think so. I mean, I've never come across such a thing.
Oh, thank you.
Are there further questions, please? All right, if there are none. So let us thank Sugandha again for very nice talk.
Thank you for your time.
So